In this session, we are going to discuss artificial basic technique, the big M technique. Okay. Now, until now, we have assumed that the given LPP was having a feasible solution and unit matrix was present in the coefficient matrix, which could be used as initial basis. But in many cases, it happens that after reducing the LPP to its standard form, we do not get the unit matrix of order M present in the coefficient matrix. In such cases, the technique of artificial basis technique is used, which was introduced by Chern and is also known as Chern's M technique or big M technique. The big M technique, the reason is M is considered to be very high value. Now let me show you one example where artificial variable will be required. Suppose this is an LPP. We wanted to find out maximum value of Z such that the objective function is x1 plus 5x2 subject to the constraint 3x1 plus 4x2 less than equal to 6, x1 plus 3x2 greater than equal to 2, and both the variable, that is x1 and x2, satisfy the non-negativity constraint, that means x1 x2 both are greater than equal to 0. So the first step as far as the simplex algorithm is concerned is to reduce or to transform this LPP into its standard form. So the standard form of an LPP is for this particular LPP is minimum of Z, which is equal to minus x1 minus 5x2 plus 0 into x3 plus x4, where x3 will be required in the first constraint and x4 will be required in the second constraint. Now notice that the first constraint is less than equal to type inequality. Therefore, we convert this inequality into an equation by introducing slack variable on the left hand side of this constraint, and therefore the resultant constraint is 3x1 plus 4x2 plus x3 equal to 6. Now in the second constraint, please notice that the inequality is greater than equal to type, and therefore the constraint now are the constraint. If you want to transform this particular inequality into an equation, we needed to subtract one variable or quantity from the left hand side. So the resultant constraint now will be x1 plus 3x2 minus x4 equal to 2, where all the variables are greater than equal to 0, but x3 is slack variable whereas x4 is surplus variable. Of course, the contribution of x3 as well as x4 should be 0, and therefore 0 into x3 plus x4. So this is now our resultant standard form of an LPP. The characteristics of standard form of an LPP right now are satisfied, right? So now we'll proceed to the next step. So that means we will write down all the values such as cost coefficient values, the decision variable vector as well as the coefficient vector. So here you can see that the cost coefficient are minus 1, minus 5, 0 and 0. So that is nothing but your C transpose. X is nothing but your column vector of the decision variable, that means x1, x2, x3, x4. As I already said, x3 is slack variable, x4 is surplus variable. Now A equal to, that means our coefficient matrix, you can see here is 3 1, 4 3, then 1 0 and 0 minus 1, right? So this is our coefficient matrix. Now since there are two constraints, that means M is equal to 2, that means we are going to need two unit vectors. Now you can see here capital A, that means the coefficient matrix is having only one unit vector, and our requirement is 2 unit vector, and therefore the initial basic feasible solution as far as this particular problem is concerned is not present. As I said, simplex method is an iterative method, and therefore we are going to need initial basic feasible solution. For initial basic feasible solution, since M equal to 2, basis will have two variables, right? Right now only one unit vector, that means the P3 associated with variable x3 is there, but we have no second variable. Since m is equal to 2, therefore basis will need two variable. Right now only one variable is present in the basis, and therefore we need to now augment the problem. We need to introduce one variable in the basis, or we need to introduce one variable in the problem which is right now not present. Such variable are known as artificial variable. They are having a very high cost, that which is denoted by generally capital M. So that is what I have written. We know that simplex method is an iterative method. The initial basic feasible solution is required with m equal to two variables. That means the unit vectors. Associated vectors are unit vectors in the basis. So to get required initial basic feasible solution, we augment the problem by introducing artificial variable. So that is basically the reason we have to introduce the artificial variable in the basis. So the resultant, now suppose this is now the our standard form. As I said, unit vector is not present, required number of unit vectors are not present in the basis, so we augment the problem. So how to augment that problem? So let me show you that. So this is basically your original objective function is minus x1 minus 5x2 plus 0 into x3 plus x4. Now you can see one more entry here. Now we have introduced x5 here. Now if you remember, the unit vector 1 0 was present, the unit vector 0 1 was missing. That means we needed one variable in the second constraint. So the next constraint, next variable that we have introduced is x5 is introduced in the second constraint. So the resultant constraint will be, first constraint will be as it is, 3x1 plus 4x2 plus x3 equal to 6, because 1 0 vector was present, so that condition was fulfilled for first vector, first constraint. In the second constraint, original constraint was x1 plus 3x2 minus x4 equal to 2. Now we have introduced one more variable there, that is x5. So plus x5 equal to 2. Of course x1 x2 x3 x4 as well as x5 should be there. So x1 x2 x3 x4 and x5 all should be greater than equals to 0, where x3 is your slack variable, x4 is your surplus variable, and x5 here which has been introduced here is an artificial variable. Now as I said, the contribution or the cost associated with x5 is very high, denoted by capital M. So you can see here in objective function mx5. The reason we are going to keep m as very high, I am going to discuss in the coming few slides. Okay, so this is now augmented problem. This is your original problem or standard form of an LPP, but this is now your augmented problem. So using now this augmented problem, we are again going to write down the values of C, capital A, X, and now we will have basis also. You can see here, this is your now augmented problem. Now you can see here the C transpose will have a value -1, -5, 0, again 0, and then capital M, right? Now the X will be x1 x2 x3 x4 x5, right? Originally it was up to only x4. Now another variable is introduced in the X is nothing but your x5, that is artificial variable. Now this is interesting, capital A, this is nothing but your coefficient matrix. Now you can see here 3 1 4 3 1 0 and 0 -1. So this is your original coefficient matrix. Now the once artificial variable is introduced here, you can have now another vector p5 will have a value 0 1. Now you can see one unit vector is present here, another unit vector is present here. That means the variable associated with p3 and p5, that means x3 and x5, will be in the basis. Therefore you can see that b is equal to x3 and x5. Of course the solution values are 6 and 2. So in this fashion we can get required number of variable in the basis, right? So by augmenting the problem by using the artificial variables. So in this case x5 was artificial variable. So in general, if we want to discuss the artificial variable technique, then the standard form of an LPP suppose is given by minimum of z, which is equal to c dash x, subject to the constraint ax equal to b, x greater than equal to 0. Now suppose this capital A, that means the coefficient matrix, does not have required number of unit vector. That means, in other words, initial basic feasible solution is absent as far as this particular standard form of an LPP is concerned. And as I already told you number of times, since the simplex method is an iterative method, we required initial basic feasible solution. Let A does not contain unit matrix, so without the initial basis we cannot apply the simplex method as it is an iterative method. So we introduce artificial vectors in the problem and formulate the LPP as. So this is your original objective function c dash x plus, then now all these variables has been introduced. Original decision variables are up to xn, that means x1 to xn, and therefore now we have introduced xn plus 1, xn plus 2, so on, xn plus m in each of the constraint. If you remember, there are m number of constraint, so we will require, if no unit vector is present in the basis, we will require m artificial variables. So the first artificial variable will be introduced in the first constraint, that will be xn plus 1. This will be introduced in the second constraint, and so on. This will be introduced in the mth constraint, right? Subject to the constraint ax is your original constraint value plus iy, that means that is nothing but your artificial variable, which is equal to b, where x is greater than equal to 0, y should be also greater than equal to 0. So where y is the vector of artificial variable, that is y will be equal to now this decision variable, that is xn plus 1, xn plus 2, so on, xn plus m. So this is basically your artificial variable vector. So that the coefficient matrix will now contain unit matrix of order m, which can be used as initial basis. M is sufficiently large, as I already told you, m is very big, so is sufficiently large such that sign of the quantity is determined by m. The sentence, the meaning of this sentence is that when we decide the entering vector, if you remember, we calculate zj minus cj. If zj minus cj is not less than equal to 0 for all j, then we search for that value of zj minus cj which is maximum. So if there are two values which are greater than equal to 0, so naturally, as I said, we are going to search for the maximum value of zj minus cj. Suppose the two values are, one is 1000 and another is m. In such case, maximum value will be decided by the m. Since m is sufficiently large, therefore we will consider m as the maximum value as compared to 1000. So that means, in other words, m will decide the sign, m will decide which value is maximum as far as the different values are concerned, right? Such a problem is called as augmented problem, right? Now the coefficient matrix has n plus m vectors. Please remember that original vectors were p1 to pn. Now we have introduced m vector starting from pn plus 1 up to pn plus m. Vectors variable associated with these vectors are nothing but our artificial vectors. The vector pn plus 1 up to pn plus m are the unit vectors which form the initial basis for the augmented problem. If there is at least one feasible solution for the problem, then that solution is feasible for the augmented problem. So in other words, if the feasible solution exists for your original problem, then that will be feasible solution for your augmented problem also. That means the solution of both the problem, that means your original problem as well as the augmented problem, are same. The simplex procedure ensure obtaining the minimum solution in which the artificial variables are either eliminated from the basis, or if they are present in the basis, they are at the zero level. So what does it mean? It means that in the final simplex table, the simplex procedure basically ensures that in the final simplex table, the artificial variable are either eliminated from the basis, and if they are present in the basis, they are at the zero level. And if this is not possible, it means that the given problem has no solution. We are going to discuss that in next slide also. If they are present at the non-zero level in the basis in the last simplex table, as I just said, then we conclude that the original problem has no solution and the constraints are inconsistent. If the artificial variable or artificial vector is eliminated from the basis, it is never selected to re-enter to the basis. Using the full artificial basis technique, approximately 2m iterations are required to reach the optimum feasible solution. So this is approximation. If there are two constraints, then 4m iterations, that means 2m, that means 4 iterations will be generally required to reach the optimum feasible solution. Of course, this is general rule. Suppose by solving the LPP using the simplex method, we arrive at a stage where Zj minus Cj is less than equal to 0 for all j. That means the optimality criteria is satisfied. In other words, this is basically our final simplex table. Now there are 2-3 situations that we wanted to discuss when Zj minus Cj is less than equal to 0 for all j. The first condition is that there are no artificial vector or artificial variable present in the basis. If no artificial variable present in the basis, then it means that the given solution is optimum feasible solution for your original problem also, right? Since the optimality criteria is also satisfied. One or more artificial variable are present in the basis, but they are at the zero level, and optimality criteria is satisfied. So optimality criteria is satisfied, but artificial variable is present in the basis, but they are at the zero level. In such situation, we conclude that the given solution is an optimum solution, but one or two constraints are redundant. Redundant matlab they are not required as far as our problems is concerned, and that particular equation or constraint can be deleted from the system or from that particular problem. Now this is a situation where one or more artificial variable are present in the basis at some positive level and optimality criteria is satisfied. That means Zj minus Cj is less than equal to 0 for all j, but artificial variable is present in the basis. Since artificial variable is present in the basis, we conclude that the given problem has no solution and the constraints are inconsistent. So that is what I have said here. If the optimality criteria is satisfied, then we conclude that the problem has no solution, either because the constraints are inconsistent or there are a solution but none of them are feasible. That means the feasible solution is missing as far as this situation is concerned. Now why we are concluding that? Since artificial variable is present in the basis, why we are concluding that the given problem has no solution, or the constraints are inconsistent, or the solution is not feasible. So that is what I have explained in the next few lines. Suppose at the stage Zj minus Cj is less than equal to 0 for all j, and one vector Pn plus 1. Suppose the Pn plus 1 is one of the artificial vector, that means Xn plus 1 is artificial variable, is present in the basis at some positive level. Suppose the value of that particular positive level is nothing but b dash n plus 1. That means this is the value of Xn plus 1. So that value, since is at the positive level, we need to use this value for the calculation of objective function. So The value of the objective function now will be z star, which is equal to c1x1 plus c2x2 up to cn plus cnxn plus m, which is nothing but the value, which is nothing but the cost coefficient of the artificial vector into, this should be bn plus 1. Okay, so this is basically the thing I am talking about, z star, which is equal to c1x1 plus c2x2 up to cnxn plus m into b dash n plus 1. Now this is nothing but your contribution due to original values in the system, because up to xn was our original decision variable. Beyond xn is nothing but the artificial variable. Out of that, the first artificial vector, that means I am talking about xn plus 1, is present at the positive level, and value of that xn plus 1 is b dash n plus 1, and therefore in the objective function its contribution will be m into b dash n plus 1. So this is nothing but your contribution due to original variables in the system, and this is nothing but the contribution due to artificial vector. In other words, z star will be equal to this particular value. Now this value, since zj minus cj is less than equal to 0, z star is nothing but your optimum value of the objective function. Now, but we have assumed that m is very large, so z star value will also be very large. Please remember that we are trying to obtain minimum value of z. Now z star value will be very large, but it is optimum value. Now suppose if x0 is some other possible solution to the problem, the value of the objective function corresponding to x0 will be naturally equal to c dash x0, which is equal to z0. Now since z star is an optimum value of the objective function, naturally z star will be less than equal to z0. But we have assumed that m is very big quantity, sign of any basically equation will be decided by m, that means z star is very large, it cannot be less than z0, so we have arrived at a contradiction. In other words, we can say that the problem has no feasible solution and the constraints are inconsistent.